We're now looking at page 2 of our notes, and we are going to look at roots, zeros, and x-intercepts. So follow along as I read what looks to be pure algebra, but once we break it down, it's not overly complicated. This key concept that we're going to look at today is this. The following are equivalent statements about real numbers, the real number b, and a polynomial. And this is the polynomial. Notice it does have a pattern, x to the n minus 1, all the way down to x to the 1, all the way down to a constant. So, in other words, standard form. In other words, standard form. Okay. Usually we have parentheses around this, so it might be easier for us to identify if it's at x minus b. But x minus b is something that's called a linear factor of the polynomial. If that's the case, if x minus b is a linear factor, then that means b is the 0. In other words, when you plug in that number b to the function, you get 0. Next, b is also a root or a solution. And lastly, b is the x-intercept when you graph the function. So what is the essential part? What is it actually saying here? In short, zeros, roots, solutions, and x-intercepts, although not perfectly analogous to each other, they are pretty much synonymous. So whenever we say zeros, whenever we say roots, whenever we say solutions, and whenever we say x-intercepts, we're saying almost the exact same thing. They are synonymous, and they're all derived from this one thing called x minus b. Usually we see it in parentheses. It doesn't have to be in parentheses, but we usually see it in parentheses, and that's called a linear factor. In this first question, we're going to be finding the zeros of a polynomial function. So that's what part A says. What are the zeros of y equals x times x minus 2 times x plus 5? And then we're going to graph the function. So part A, we're going to find the zeros. Part B, we're going to graph it. Well, how do we find the zeros? If we review and look at yesterday's review, we're going to use this magical property, the zero product property. Without words, I'm going to write it over here, and I want you with your partner to express it in words. So if a times b equals 0, then one of those has to be 0. The factors have to be, one of them has to be 0 at least. So how do I use it in this situation? Well, to find the zeros, I have to replace the y with a 0. So I'm just going to write it out. X minus 2 times x plus 5. Now the zero product property says one of those factors has to be 0. So I'm going to break this up. Either x is 0, or x minus 2 is 0, or x plus 5 equals 0. Notice there is no limitation on the number of factors you could have. This could go out to a gazillion different factors, and each one of them we would set up to be equal to 0. And now we just solve individually. X is 0, that's already done. So here x is 2 when I add 2 to both sides. And here, x is negative 5. So here are my zeros, which I'm going to transfer down here real quick to be 0, 2, and negative 5. So now, here's the key, folks. We have the zeros, which means we also have the x-intercepts. Hush. I won't tell anybody, but we now have the x-intercepts of the graph, which means I now have 3 points. Now, notice over here, the scale is a little bit ugly. The scale is not counting by ones, it's not counting by twos, it's counting by 2.5s. That's just an accident when I cut and pasted this. So that means when I graph the zeros, one of the zeros is a -5, so that's going to be right here, exactly between 0 and -10. Another one is the 0, and the other one is a 2, and that's going to be funny because it's not exactly on. It's got to be right about here. So I do apologize for that. I didn't mean to have it split up into 4s. I meant it to be split up into 5s. Let's see what we know. We know because this is a function, and specifically, do we know what type of function is it? What degree is it? What is x times x times x? X times x times x. That is x to the third. X times x times x is cubic. So, we know because it's cubic, its basic shape will be like this or down, like that. So because A is positive, we know that it's going to be down up. It's going to be a down up. So the end behavior is down up. Now I'm going to graph this real quick just to show you some sketches, but I'm also going to point out to you there are an infinite number of opportunities. So watch. The graph could look like this. It could start low and come very sharp, and then come like this and be very shallow and then go up. That could be one. It could be this, where this one comes very high and this one's very shallow and it goes up. Look, I have an infinite number of options to choose from. They both could go high and very low and then back up. I just don't know. So the key is I need more data. I need more data, which means I already know that my function comes from down here. I already know my function crosses these 3 points, and I know my function keeps going that way. But I don't know how it behaves in between. I don't know how it behaves in between. It's kind of like when kids go to school. Mom and dad knows what they're like at home, but in between, what are they like? So, let's go ahead and find, I need to see the behavior of the graph when it's in between here, and the behavior of the graph in between here. So, if this is -5, and this is 0, and this is +2, what would be a good value of something in between here? So, if I select a number like this, a -3, that'll tell me what the behavior's like somewhere inside there. And what if I select another one right here? X is 1. That's going to tell me what the behavior is down here going to be like. So, here's step part C. I have to find additional points. I chose those points by looking between the zeros. How did I find additional points? I looked between the zeros. Between the zeros. Between the zeros. So, when you substitute a -3 in, it's going to look like this. Let me get back to my original function. I have to put a -3 here, here, and here. By the way, you could have chosen other points. You could have chosen a -2. You could have chosen a -1. I just chose -3 because it's almost spot on in the middle. Okay, so let me see here. Substituting a -3 in. Y equals -3 times -3 minus 2 and negative 3 plus 5. So I'm evaluating the point, the function, at negative 3. I'm going to finish up here. The negative 3 comes down, the negative 5 comes down, and the positive 2 comes down. So this gives me a positive 30. So how do I interpret that? One additional point is negative 3, positive 30. Negative 3, positive 30. In other words, in between these two zeros right here, in between these two zeros, my function shoots up quite a bit, all the way up to here. The function shoots up quite a bit. Now, what's the behavior of the function when it's between the 0 and the 2? I'll know that, or at least partially I'll know that, when I substitute in x equals 1 to see what happens there. So y equals 1 times 1 minus 2 and 1 plus 5. Simplifying these, I get 1 times negative 1 times 6, so I get negative 6. So what's the point? 1, negative 6. So relative to the other point, this one drops down, but not by much. It only drops down to about here. So globally, let's see what happens. The function starts at infinitely low here. It comes up, stops about 30, comes back down, shoots through the 0, hits here, the negative 6, comes back up through the 2, and up forever. So here's the trick. Use a pencil. Because watch how bad my graph is going to be the first try. I'm going to shoot it up, and oops, I'm already slopped, and I've got a snap. Okay, very ugly. So I have an undo button. You are going to need to use your eraser. Please make it look somewhat good. And if it takes you to do it a couple tries, then good. Which that's not good, so let me try it again. Still not good. Better.